Right now, whatever device you're using to watch this, a silent, constant negotiation is happening inside it. Every single second, your computer is deciding what information deserves to sit in the fastest, most expensive memory available, what can wait in slower storage, and what gets thrown away entirely to make room for something more urgent. You never see this decision happen. But how? Well, your operating system makes that decision thousands of times per second, is one of the biggest reasons your computer feels fast or feels sluggish. And it turns out Windows and Linux make fundamentally different choices about how to handle it. That difference isn't just an abstract academic curiosity for computer science students. It's the reason two machines with genuinely identical hardware specifications, the same processor, the same amount of RAM, the same storage drive, can feel noticeably different to actually use day to day. And it's the reason server administrators managing serious workloads increasingly have strong, informed opinions about which operating system's memory management they trust more for their specific use case. Let's start with the basics, because understanding the actual hierarchy here makes everything else in this video make sense. And it's worth building this foundation properly before comparing how the two operating systems handle it differently. Inside your computer, there's a layered system of memory and storage, and each layer trades speed for capacity in the opposite direction. At the very top sits your processor's cache, tiny pools of memory built directly onto the CPU chip itself, split into levels called L1, L2, and sometimes L3. L1 cache is blisteringly fast, capable of being accessed in a matter of nanoseconds, but it's also tiny, often just tens of kilobytes. It holds the absolute most immediately needed instructions and data the processor is working with right this instant. L2 and L3 cache are progressively larger and progressively slower, acting as a buffer between that lightning-fast L1 cache and the next layer down. That next layer is RAM, your system's main memory, measured in gigabytes rather than kilobytes or megabytes. RAM is dramatically slower than CPU cache, but it holds vastly more data. The actual programs you have open, the files you're editing, the browser, tabs sitting in the background. RAM is also volatile, meaning the instant your computer loses power, everything stored in it disappears completely. That's the trade-off. RAM is fast enough to keep your open programs running smoothly, but it forgets everything the moment the lights go out. Below RAM sits your storage, your SSD, or on older machines, your hard disk drive. This is where everything permanent actually lives. Your operating system, your installed programs, your documents, your photos. Storage is dramatically slower than RAM, but it's non-volatile, meaning it keeps everything intact, even when the power is completely off. Solid-state drives, built on flash memory chips with no moving parts, have become the dominant choice for both Windows and Linux machines in recent years, specifically because they close a huge portion of that speed gap compared to older mechanical hard drives, which relied on physically spinning magnetic platters and a moving read-write arm, introducing real, measurable delays every time data needed to be located and retrieved. It's worth spending a bit more time on that CPU cache layer specifically, because most people have heard the term without ever really understanding what makes it so dramatically faster than everything below it. The reason L1 cache can be accessed in a matter of nanoseconds isn't just that it's smaller. It's built directly into the same physical silicon as the processor cores themselves, using a different, faster, more expensive type of memory technology called SRAM, static random access memory, rather than the DRAM, dynamic random access memory used for your system's main RAM. SRAM doesn't need to be constantly refreshed electrically the way DRAM does, which makes it faster to access, but also considerably more expensive to manufacture per unit of capacity, which is exactly why you get kilobytes of L1 cache instead of gigabytes. That fundamental cost versus speed trade-off is the same underlying principle driving every single layer of this entire memory hierarchy. From CPU cache all the way down to your storage drive, faster technology costs dramatically more per gigabyte. So computer architects build a layered pyramid, keeping a small amount of the fastest, most expensive memory as close to the processor as physically possible, backed by progressively larger and progressively cheaper, slower layers underneath. So that's the hierarchy. Blazing fast, tiny CPU cache, moderately fast, moderately sized RAM, and slower, enormous storage sitting underneath both. Every operating system's core memory management job is deciding constantly and automatically what data deserves to sit at each layer of that hierarchy at any given moment, because keeping frequently needed data as close to the processor as possible is one of the single biggest levers determining how responsive your entire system feels. Here's where the story gets genuinely interesting, because this is exactly the part where Windows and Linux start making noticeably different decisions, and those differences show up in ways you can actually observe on your own machine if you know where to look. Let's talk about how Windows approaches the exact same underlying problem, because the philosophy is genuinely different, not just cosmetically different, and it's worth understanding the reasoning behind it rather than just the outcome. Modern Windows uses a background service called sysmain, which most longtime Windows users will recognize by its older name, Superfetch. Sysmain's job is to watch which applications you use most frequently and proactively preload pieces of those programs into RAM before you even ask for them, on the theory that if you tend to open your web browser and email client first thing every morning, Windows might as well have them partially loaded and ready before you click the icon. That's a genuinely clever idea in principle, designed to make your most commonly used programs feel like they launch instantly. But here's the practical consequence of that approach, and it's worth stating in concrete numbers rather than abstractly. A Windows machine with 32 gigabytes of RAM installed will frequently show 8 to 10 gigabytes of that memory already in use, sitting idle, before you've opened a single program yourself. That's not a bug or a memory leak. It's sysmain doing exactly what it's designed to do, filling available RAM with predictively preloaded application data on the assumption that unused RAM is wasted RAM. On top of that predictive preloading, Windows also begins writing to its page file, a reserved section of your storage drive used as overflow space when RAM runs low, starting from the moment your computer boots up, regardless of whether your system is actually running low on memory at that point or not. Now let's talk about how Linux approaches the exact same underlying problem, because the philosophy is genuinely different, not just cosmetically different. Linux uses something called the page cache, which serves a broadly similar function to what sysmain is trying to accomplish, keeping frequently accessed data available in fast RAM rather than constantly rereading it from slower storage. But Linux's page cache tends to be far more aggressive and, importantly, far more transparent about how it operates. Recent versions of the Linux kernel use a memory management system called MGLRU, short for multi-generational least recently used, which tracks memory pages across multiple generations of recency and reclaims genuinely idle pages more efficiently than older approaches did. The practical result is that Linux systems tend to show a meaningfully lower baseline memory footprint at idle compared to an equivalent Windows machine, while still aggressively using spare RAM for legitimate caching purposes rather than leaving it sitting completely empty. The real difference worth understanding here isn't really about which operating system uses more RAM at idle, though that's the part that shows up most visibly in simple benchmarks. It's about transparency and control. If you open a terminal on a Linux system and run a simple command like free, you'll see memory usage broken down into categories that actually mean something. How much RAM is truly free and untouched? How much is being used by actual running programs? And critically, how much is being used for cache and buffers? Memory that's technically occupied but instantly reclaimable the moment a running program actually needs it. Linux draws a clear, visible line between memory that's genuinely unavailable and memory that's just being put to good temporary use while it waits to be needed elsewhere. Windows equivalent reporting, by contrast, has historically been considerably murkier from a typical user's perspective. Task Manager shows you a single memory usage percentage, and figuring out how much of that number represents genuinely committed memory versus sysmain's predictive preloading versus other background caching requires digging into considerably more advanced diagnostic tools than most users will ever bother opening. That opacity feeds directly into one of the most common, mildly infuriating experiences Windows users have had for years. Opening Task Manager, seeing memory usage sitting at 70 or 80% on a machine that's supposedly just sitting idle and having no easy built-in way to understand whether that's actually a problem or just Windows quietly doing its job in the background. It's worth being fair to Microsoft's underlying reasoning here, because sysmain's core idea isn't a bad one on its own technical merits. Preloading frequently used applications genuinely can make everyday common workflows feel snappier for average users. And Windows' approach was specifically designed around the assumption that most consumer machines have RAM sitting mostly idle anyway. So proactively using more of it for predictive caching is a reasonable trade to make by default. That reasoning holds up better on a modern machine with abundant RAM than it does on an older or more memory-constrained system, where that same aggressive preloading behavior can end up competing for resources against whatever the user is actually trying to do in that moment. It's worth talking about what happens on each operating system when memory pressure gets genuinely severe, not just moderately high, because this is another area where the underlying philosophy shows up in a very concrete, user-visible way. When Linux runs completely out of both RAM and swap space, with no more memory available anywhere in the system, a mechanism called the OOM killer, short for out-of-memory killer, steps in and forcibly terminates whichever running process it calculates is the least critical or most memory hungry, specifically to free up enough memory to keep the rest of the system stable and responsive. It's a blunt, sometimes frustrating mechanism. The exact process it chooses to kill isn't always the one the user would have picked themselves. But it's also a documented, well understood, and to some degree configurable part of how Linux behaves under genuine memory exhaustion, with system administrators able to adjust which processes are considered higher or lower priority for termination if the default behavior doesn't suit their particular workload. Windows handles this same extreme scenario somewhat differently, generally leaning harder on the page file as a buffer before resorting to anything as drastic as forcibly closing applications. And when a Windows system does become severely memory starved, the more common user experience is significant system-wide slowdown and unresponsiveness, rather than a specific application being killed off cleanly. Neither approach is objectively wrong. They reflect different priorities. Linux favoring a faster, more decisive recovery back to a stable, responsive state, even at the cost of losing unsaved work in whatever process gets terminated. Windows favoring an attempt to keep every running application alive longer, even if that means the entire system becomes sluggish and difficult to use in the meantime. But it's a genuinely different philosophy about how to handle an operating system's absolute worst-case memory scenario, and it's one more example of the same underlying pattern showing up again. Linux tends to expose the mechanism and hand you some level of control over it, while Windows tends to handle it automatically, behind the scenes, with considerably less visibility into exactly what's happening or why. Let's talk about swap and paging specifically, because this is another area where the two operating systems' philosophies diverge in a way that matters for real-world performance. When RAM genuinely fills up, both Windows and Linux fall back on writing some memory. Content's out to storage temporarily, freeing up RAM for more urgent tasks. On Windows, this happens through the page file, and as mentioned, Windows begins writing to it from boot, regardless of actual memory pressure, treating it more as a constant, low-level background behavior than a last resort. Linux's approach to the equivalent concept called swap is more directly tunable by the user through a setting called swappiness, a value between 0 and 100 that controls how aggressively the kernel favors swapping inactive memory to disk versus keeping it in RAM, even under moderate memory pressure. A lower swappiness value tells Linux to strongly prefer keeping data in RAM and only swap to storage as an absolute last resort, which matters enormously on modern systems where storage, even fast SSD storage, remains meaningfully slower than RAM. That kind of granular user-adjustable control simply doesn't exist in an equivalent, easily accessible form on standard consumer Windows installations, where the page file's behavior is managed automatically with comparatively limited user-facing configuration options. It's worth adding some historical context here too, because the stakes of all this memory management discussion have actually shifted over the past decade in an interesting way. Back when mechanical hard disk drives dominated consumer computing, the gap between RAM speed and storage speed was so enormous that getting caching decisions right or wrong made an absolutely massive difference in perceived performance. A cache miss that forced your system to go all the way down to a spinning hard drive could introduce a delay measured in tens of milliseconds, an eternity from a processor's perspective. The rise of solid-state drives over the past decade has narrowed that gap considerably, since flash memory storage responds dramatically faster than spinning. Magnetic platters ever could. That narrowing gap has made memory management differences somewhat less dramatic in raw, everyday responsiveness than they would have been a decade ago, but it hasn't eliminated the difference entirely, and it's actually made the more granular, high-performance computing side of this comparison, the kind involving high core count servers and heavy allocation workloads, more relevant than ever, precisely because modern hardware has gotten fast enough that the software layer managing it has become a comparatively larger share of the total performance equation. There's a genuinely interesting real-world example of these philosophical differences playing out that's worth walking through concretely, because it's not just an abstract technical distinction. It shows up in everyday applications people actually use constantly, because it's not just an abstract technical distinction. It shows up in everyday applications people actually use constantly. Modern chat and communication apps built on a framework called Electron, which essentially bundles an entire miniature web browser inside every single app, have become one of the biggest sources of memory bloat on both operating systems. Discord's desktop client on Windows has been documented reaching around 4 gigabytes of RAM usage under fairly ordinary real-world conditions, dramatically higher than the company's own marketing claims of using under 1 gigabyte. Interestingly, Discord's own engineering team has apparently had to build in an automatic restart mechanism that silently relaunches the app after periods of idle time, specifically when its memory usage climbs past that 4 gigabyte threshold, essentially patching over the underlying memory management problem rather than solving it directly. Microsoft Teams, despite having migrated away from the older Electron framework toward a newer system called WebView 2, still commonly sits around 1 gigabyte of RAM usage even while sitting completely idle in the background. On equivalent Linux systems, these same categories of Electron-based applications generally consume noticeably less memory, a difference that traces back directly to how much more aggressively and efficiently the underlying operating system reclaims memory those apps aren't actively using at any given moment. It's worth mentioning a genuinely new technical development here too, because it shows this isn't a static, settled comparison. Both operating systems keep evolving. The Linux kernel version 6.18, released in November 2026, introduced a feature called Sheaves, a per-CPU caching layer specifically designed to speed up a category of internal memory allocation called slab allocation. On servers with a very high number of processor cores, 64 or more, a global lock used to coordinate this kind of low-level memory allocation had increasingly become a performance bottleneck, since every core competing for the same lock during frequent small memory allocations and delocations creates contention that slows the entire system down. Sheaves cache these allocations at the individual per CPU level instead, cutting down on that lock contention and meaningfully speeding up both the allocation and freeing of memory under heavy server workloads. Windows Server, by comparison, doesn't currently expose an equivalent tuning mechanism for this specific kind of low-level allocation behavior. Its allocator improvements arrive bundled into broader, more opaque system updates, without giving system administrators the same kind of direct, granular configuration control over allocation caching strategy that Linux increasingly provides at the kernel level. That distinction matters more than it might sound like to anyone who isn't personally managing a server farm, because it reflects a broader pattern in how these two operating systems treat their most technically sophisticated users. Linux's approach to memory management keeps adding new, genuinely inspectable, genuinely tunable knobs that a system administrator can study, adjust, and optimize for their exact workload. Windows' approach tends to bundle these same categories of improvement into large, cumulative updates where the underlying mechanism is deliberately abstracted away from the end user on the assumption that most users would rather have sensible defaults handled automatically than a long list of settings to understand and configure correctly themselves. That's genuinely a defensible design philosophy, and it's worth being fair about that rather than treating it purely as a shortcoming. Most ordinary computer users have no interest in manually tuning swappiness values or understanding slab allocator lock contention, and Windows' more automated, less exposed approach to memory management genuinely serves that much larger audience well in the overwhelming majority of everyday use cases. The trade-off only becomes a genuine disadvantage for the specific, narrower population of power users, developers, and system administrators who actually want or need that deeper level of visibility and control. But for exactly that audience, and it happens to be a significant and vocal audience within the broader tech community, Linux's more transparent, more configurable approach to memory management represents a real, tangible advantage, rather than just a philosophical preference. Let's bring storage back into this picture too, because memory management and storage performance are more tightly connected than they might initially seem. Every time your operating system decides that a particular piece of data isn't urgent enough to keep in RAM, it gets written out to your storage drive instead. And every time you open a file or launch a program, your operating system has to decide whether that data is already cached somewhere in RAM or needs to be freshly read from storage. A more aggressive, better tuned caching system directly reduces how often your storage drive actually needs to be accessed at all, which matters even on modern SSDs, because avoiding an unnecessary storage read is always faster than even the quickest possible storage read. This is exactly why Linux's more aggressive, more efficient page cache behavior translates into a real, measurable performance advantage in certain workloads. Not because Linux storage drivers are inherently faster at the hardware level, but because Linux's memory management more effectively avoids needing to touch storage in the first place for data that's been recently used and is likely to be needed again soon. So where does this leave you practically if you're trying to decide what any of this actually means for your own everyday computer use? If you're running Windows and you've ever been mildly alarmed by Task Manager showing memory usage sitting at 70 or 80% while your computer feels perfectly responsive, now you know why. That's very likely sysmain doing exactly its job, predictively caching your commonly used applications rather than any kind of problem you need to address. If you're curious about switching to Linux, or you're already running it, understanding tools like the free command and the swappiness setting gives you a genuinely useful, transparent window into exactly how your system is managing its resources, a level of visibility that simply isn't as readily available in a standard Windows installation without digging into more specialized diagnostic tools. It's worth giving you something concrete to actually try, rather than leaving all of this purely theoretical. If you're running Linux right, now open a terminal and type free H, and you'll see your memory broken down into total, used, free, shared, buff, pot, or cache, and available columns, with that available figure representing the real number that actually matters day to day. How much memory your system could make available to a new program right now, including whatever's currently sitting in reclaimable cache. Windows, the closest equivalent, requires opening the resource monitor rather than the basic task manager view. And even then, the breakdown between hard-committed memory and standby cached memory takes more digging to interpret correctly than the Linux equivalent does, precisely because Windows wasn't designed with the same assumption, that ordinary users would want or need to inspect that distinction themselves. None of this means Windows memory management is fundamentally broken, or that Linux is automatically the better choice for absolutely everyone in every situation. Windows' more automated, more abstracted approach genuinely serves the enormous majority of casual computer users perfectly well, precisely because most people neither want nor need to understand the difference between committed memory and reclaimable cache. But for anyone who's ever wondered why their supposedly powerful, well-spec'd Windows machine seems to be using an unexplainably large chunk of its memory before they've even opened anything, or why, server administrators managing high core count workloads increasingly gravitate toward Linux. For exactly this category of fine-grained memory tuning, the underlying answer traces directly back to two fundamentally different philosophies about how much visibility and control to hand over to the people actually using the machine. It's worth ending on the bigger picture this connects to, because memory management is really just one small technical example of a much larger pattern this channel keeps coming back to. Every layer of a modern operating system, from how it handles your files to how it handles your memory to how it handles your privacy, reflects an underlying choice about who that system is really. Designed to serve the user who wants to understand and control exactly what their own machine is doing, or the average user who just wants sensible defaults, handled automatically without ever needing to think about it. Windows has increasingly leaned toward the second philosophy across nearly everything it does, memory management included. Linux, across nearly every layer of the stack, keeps leaning toward the first, handing over the mechanism along with the defaults, for anyone curious enough to actually go looking. If you want to see how this connects to the bigger pattern we've covered on this channel, Windows increasingly making decisions on your behalf across nearly every layer of the operating system, from bundled AI features to background telemetry to now the very memory management running underneath everything else you do. The other videos covering those stories are linked right here. Let me know in the comments if you've ever actually opened Task Manager or the free command, specifically to investigate exactly where your memory was going and what you found. Subscribe if you want to keep learning exactly how much is happening under the hood of your computer that you were never really shown in the first place.